In this video, we'll solve our simple example in LibreOffice. Go ahead and open the spreadsheet IMRT Simple Example. At the top of the spreadsheet, you should see our data. For each beamlet and each voxel, we have the dose that beamlet gives to that voxel at unit intensity. So we have this data for voxel 1, voxel 2, voxel 3, all the way up to voxel 9. Each row corresponds to one of the 6 beamlets. This is the data that we saw in the slides in the previous video. Below the data, we've outlined our decision variables, which are the intensities of the beamlets. So for beamlets 1 through 6, we have one decision variable. These 6 decision variables are outlined in yellow. Right now, the decision variable cells are blank because the values will be filled in by Solver. Below the decision variables, we have our objective. Our objective is to minimize the total dose to healthy tissue. The healthy tissue voxels are voxels 1, 3, 5, 6, and 9. So let's go ahead and build our objective in the blue cell here. So first, we want to add up the total dose that each beamlet gives to voxel 1. So here, we'll use the function that we used in the previous lecture, sum product. So type an equals sign and then sum product and select all of the decision variables, semicolon, and then all of the doses. This will add up the total dose that beamlet 1 gives to voxel 1, plus the total dose beamlet 2 gives to voxel 1, plus the total dose beamlet 3 gives to voxel 1, etc. Now we want to repeat this for voxels 3, 5, 6, and 9, the other healthy tissue voxels. So go ahead and type a plus sign, and then sum product, again the 6 decision variables, semicolon, and this time select the dose data for voxel 3. Now let's repeat this again, but this time for voxel 5. So sum product, and then the decision variables, and the dose data for voxel 5. Now for voxel 6, sum product, the decision variables, semicolon, and the dose data for voxel 6. And lastly, we're going to add the sum product of the decision variables, semicolon, and then scroll over to voxel 9 and select the dose data for voxel 9. Close the parentheses and hit enter. You should see that the objective has a 0 right now because none of our decision variable values are filled in. When Solver fills in our decision variables, our objective value will be here. Below the objective is our constraints. The first 4 constraints make sure that each voxel of the tumor is getting a dose of at least 7. The last constraint makes sure that the spinal cord receives a dose of no more than 5. Let's go ahead and construct our constraints. For the first 4 constraints, the left-hand side is going to be the total dose that voxel of the tumor gets. So for voxel 2, we have the left-hand side is equal to the sum product of the decision variables, semicolon, and then the data for voxel 2. Close the parentheses and hit enter. We want to make sure that this value is greater than or equal to 7. Now let's repeat this for voxel 4. So equals sum product, and then in parentheses select the decision variables, semicolon, and the data for voxel 4. Again, we also want this one to be greater than or equal to 7. Now let's repeat this for voxel 7. So sum product of the decision variables, semicolon, and then the data for voxel 7. Again, greater than or equal to 7. And lastly, for voxel 8, we want the sum product of the decision variables and the data for voxel 8 this time to also be greater than or equal to 7. And our last constraint, we want to make sure that the total dose to voxel 5 the spinal cord voxel, so sum product of the decision variables, and then the data for voxel 5 is less than or equal to 5. The remaining constraints we have are the non-negativity constraints, which we'll add in directly in the solver. So now go ahead and go to the Tools menu and select Solver. The Solver window should pop up. First, we need to tell Solver what our objective is. So go ahead and delete what's in Target Cell, and making sure that your cursor is in Target Cell, select the blue Objective cell. Now we want to change maximum to minimum because we're trying to minimize the total dose to healthy tissue. And our decision variables should be the 6 yellow cells. Now let's add in our constraints. So in the first cell reference box, let's select the first 4 constraints. Because they're all greater than or equal to constraints, we can add them in together. And change the operator to greater than or equal to, and then in value, select the 4 right-hand sides. Now let's add in the spinal cord constraint. So in the next cell reference box, select the spinal cord left-hand side, make sure that operator is less than or equal to, and in the second value box, select the spinal cord right-hand side. Now let's add our non-negativity constraints. So in the cell reference, just directly pick the 6 decision variables. And make sure the operator is greater than or equal to, and the value should just be 0. Now in the options, make sure you've selected the linear solver and click OK. Now go ahead and hit Solve. You should see a solving result that says Solving successfully finished, result 22.75. That's the optimal objective function value. Go ahead and select Keep Result. Now let's take a look at our solution. So the optimal solution is to have beamlet 1 at an intensity 2.25, beamlet 2 at an intensity of 0, beamlet 3 at an intensity of 3, beamlet 4 at an intensity of 3.5, beamlet 5 at an intensity of 2.5, and beamlet 6 at an intensity of 0. This makes sense because beamlet 2 goes across the spinal cord, and beamlet 6 only goes down healthy tissue voxels. And if we look at our constraints, we can double check. That each tumor voxel spinal cord is receiving a dose of 5, which was the maximum possible dose. In the next video, we'll see an example of a real problem and how big the problem is on an actual tumor case.